Okay, so we're in chapter 1, section 3 now. These are all analytical, evaluating limits analytically. And the basic comes down to a couple of different choices. One is, if the function exists at the point, most of the time, just normal functions, the limit is the function. The special cases you have is where you end up with an indeterminate result, where you plug the number in, the limit, and then it gives you 0 divided by 0, which is indeterminate, and then you have to do, if you use either, what do they call it? Simplification by, I forgot what the name is here, dividing out technique. Or you can use rationalization, or you can use the squeeze theorem. Those are the main ones that are important. So a lot of these are going to be really simple. So the first thing you always want to do is just plug the number in and see what you get, unless it's a piecewise function. And they put those in there just to, I guess, make sure you understand it more completely, but you can do 99% of the calculus without having to make it complicated, as I mentioned earlier. Okay, so we're going to start off with problem number 7, which is the limit as x goes to 0 of the quantity 2x minus 1, which, so this is the function f of x is equal to 2x minus 1, which, you know, is the same as y is equal to 2x minus 1. So if you plotted that, it would be a line with a slope of 2 and a y-intercept of -1. And it's continuous. Remember, continuous means that if you put a pen down, you can draw a line continuously without having to lift it up. So in this case, you just plug the number in. So the limit as x goes to 0 is the same as the function. So we would say f, the function evaluated at x equals 0, is equal to 2 times 0 minus 1, which is -1. So the limit is just -1. You can kind of think of it, here's our xy axis. We drew this function, y-intercept of -1, slope of 2, so it would go something like this. So it would be that. And so the limit as x approaches 0, so here's x equals 0, is the function. Simple. Chapter 1, let's keep saying 3. Chapter 1, section 3, problem number 13. So let's write it down. The limit as x approaches 2 of function 1 over x. So if you think about the reciprocal function, which is what that is, and we look at x greater than 0, it looks something like this. So as x goes to 0, the function goes to infinity, and the limit actually does not exist at x equals 0. So that's the function. I just drew it dashed lines because it's hard to draw curved lines with this arrangement. Okay, so the function does not exist at x equals 0, and the limit does not exist, but when you go to x equals 2, so somewhere over here, and x is equal to 2, y is equal to 1 over 2, which would be a half. And so again, this is a continuous function except at x equals 0. And so the function, the limit of this function as x approaches 2 is just the value of the function. So we could say that the value of the function at x equals 2 is equal to 1/2, and therefore the limit is 1/2. Okay, we're on to number 45. So we're getting into, I think we're getting into somewhere you have indeterminate results. So it says find the limit if it exists. Write a simple function of degrees. Okay, so the first thing we're going to do is we're just going to plug the numbers in. The value of x. So it says limit as x approaches -1 of x squared minus 1 divided by x plus 1. So first thing you do, plug in what is f of -1. That's the question. F of -1 is negative 1 squared minus 1 divided by negative 1 plus 1. Okay, so what's that? Well, 1 minus 1 over negative 1 plus 1, which is 0 divided by 0. So here's our indeterminate case. Now just because the function is indeterminate at that point doesn't mean that the function does not exist. It just means that, well, the function does not exist, but doesn't mean the limit does not exist. So what we do is, typically when you have a rational function here, you just factor out. When this happens, that means that if you factor out these, there should be something that cancels out. So we go down here and we say, okay, can we factor the numerator? Yes. X plus 1 times x minus 1 divided by x plus 1. So what we find out is that that cancels out with that, and that's why you get the indeterminate part. Because when you stick negative 1 in, that goes to 0, that goes to 0. This goes to non-zero, but when you multiply 0 times a non-zero number, you get 0. So what that means is that the limit does exist in this simpler form. So then you can just plug it in. So we just plug in negative 1, and so that's just f of negative 1. So you put negative 1 minus 1 is equal to negative 2. So that's how you do it analytically. So let's just confirm this by doing it graphically. And what I'm going to do is I'm going to, screen's going to go blank. I need to open up my graphing program so I can switch over to that, which I will now. So all we'd have to just plug in that original equation, not the simplified one, but the other original one. So we'd have x squared minus 1 divided by x plus 1. And if we plot this, and then we look at x equals negative 1, x equals to negative 1 is right there, and y is equal to negative 2. So even though the function does not exist at this particular point because it's indeterminate, the limit exists, and when you look at it graphically, it looks like it is there, but it's really not there. Because if I plotted both those functions, the original function, and use a semicolon to separate the equations, just x minus 1, which is a simplified version, you'll see that it's the same curve, except for that one point. You would, if you were doing that, you would put a little open circle right here. Okay, now we're going to problem 46. Similar kind of thing, so let's write it down. Limit as x approaches negative 1 of 2x squared minus x minus 3 divided by x plus 2. Just because it's a rational function doesn't mean that it's indeterminate. You always have to plug the number in to find out. So let's do f of negative 1. So we get 2 times negative 1 squared minus a negative 1 minus 3 divided by negative 1 plus 1. And so negative 1 squared is positive 1, so positive 1 times 2 is 2. Negative 1 times negative 1 is positive 1. Subtract 3 divided by this, and you can see it does become indeterminate. So that means that if we factor this, we should have that. Kind of helps you figure out almost what to factor. So if you factor the numerator, we know that one term is going to be x plus 1. Has to be if you get a 0 here. And the other term is going to be 2x and something. So there's a couple of ways you could do it. One is you could say, oh, well, I got negative 3 here at the end, so if this is positive 1, then it has to be negative 3. Let's just check to see if that's true or not. See if it worked out. So x, so you get 2x times 2x is 2x squared, plus 2x, 1 times 2x, and then you get negative 3x, and you get positive 1 times negative 3, which is negative 3. So you get 2x squared minus x minus 3. So it is. So check. It has to be. I mean, there's no way it couldn't work out. Okay, so you can factor it. So all you have to do is then rewrite the original limit as x plus 1, 2x minus 3 divided by x plus 1. These two cancel out. And remember, back to pre-calculus, you think, well, do they cancel out? Does that mean I don't have to worry about them? And the answer is no, you still have to worry about them. Because we couldn't just say, well, we're going to replace the original expression by 2x minus 3. We could everywhere except one point, and that point would be x equals negative 1. So if we were to compare, say, this versus the cancel out version, if I were to plot this function and this function, they would look exactly the same, except that x equals negative 1. And there you would have a circle. So I don't know what this actually looks like. So it's a parabola. And I don't know exactly what it looks like, but I'm just going to draw a parabola. So let's say it's like this. And let's, if we plotted these two, which we're going to do in a second, they're going to look exactly the same. The only difference is that, say x equals negative 1, we put a circle there, which indicates that the function does not exist there, but it exists everywhere else. Okay, let's evaluate the limit. So now that we have something that is determinate and not indeterminate, then you just plug it in. So the limit of this function is going to be the same as the limit of this function. So you stick it in there, negative 1 in, and you get negative 5. So that would be the limit. And you can verify that by going to the graphing program and plotting the original function, which we'll write this out. So it's 2x squared minus x minus 3 divided by the quantity x plus 1. So we plot this thing out. So it looks like almost a straight line. Well, it is a straight line. So let's zoom out a little bit. So it is a straight line. Even though the numerator is a quadratic equation, the denominator is a linear equation, and the ultimate answer is linear. So it is a straight line. And you can see that at x equals negative 1, which is right here, you come down and you get y is equal to negative 5. So the function does not exist at this point, right here, but the limit does exist, because if you come from the left-hand side, you approach 5. And if you come from the right-hand side of negative 1, you approach 5 as well. So the limit does exist, and it's equal to the function that you get when you simplify it. So the simplified expression is, what was it, 2x minus 3. So if I plot that, you'll see it's the same graph. They're right on top of each other, and they look exactly the same. They are the same, except at that one particular point. Okay, now we're on to problem number 49. So we have the limit as x approaches 5 of this thing, x minus 5 over x squared minus 25. So again, just because it's a rational function doesn't mean that the limit does not, or the function does not exist. I mean, at every point except for probably one point, this thing is going to just be plug in and you're going to get the answer. So again, the first thing you want to do is evaluate the function at the value, the x value you're trying to find the limit. So we stick 5 in there. And in this case, actually is indeterminate, 0 divided by 0. So at that point, you know that you have to factor the original rational function, and you'll find out that there is a common term. And it's going to be x minus 5 because it has to be there, or we wouldn't have got 0 divided by 0. So the other factor is x plus 5. So we cancel out. So the original limit, the limit here of this function is also the same as the limit as x approaches 5 of what I have left over, which is 1 over x plus 5. So we plug that in to the equation and you get 1/10. Now if I were to say, what is the limit as x approaches -5? Well, I'd just plug -5 in and see what happens. So I'd have -5 minus 5 divided by -5 squared minus 25. And so if I just plug it in there, you get -10 divided by 0. So that the function does not exist at x equals -5, and therefore the limit does not exist at that particular point. The function does not exist. If the function does not exist because it goes to infinity, the limit's not going to exist at that particular point. Okay, this is problem number 53. So it's a case of, well, a possible case. We don't know until we actually plug the number in there, but it's a possible case of rationalization because using rationalization because we have square root terms. So if you plug 0 in, you'll get 0 plus 5, which is 5. So you get the square root of 5. Subtract the square root of 5. That gives you 0, and you get 0 in the denominator. So it is indeterminate. Therefore, we can use the rationalization. So I'm going to just take the expression, the original expression, like that, put it in parentheses, multiply by the proper modified version where we change the second term to be positive. And we multiply and divide by the same quantity. And if we plotted this function and we plotted this function, they would be exactly the same, because the only thing that would make it different is if the domain of this was different than the domain of that. And the domain here is that is more restricted. So if you look at this, x cannot equal 0. Well, yeah, because then you'd have an indeterminate result. And you can't let x be less than -5, because if it was, then you'd have a negative square root. So the -5 applies, and you don't have to worry about x equals 0. So this is not any more limiting than this one is. Therefore, the domain of this is the same as the domain of that. Now, if it had, if you had something like x plus 3 here, then this would, by multiplying by square root of x plus 3 plus, say, the square root of 5, same thing in the denominator, then this would have a more restrictive domain, and so you'd have to be careful about that. Anyway, you don't really need to worry about that. So we're not really changing things, except we are going to be able to remove ultimately what we're trying to do is actually get this result, so it is determinate. Okay, anyway, use FOIL. So the first and the first terms multiply together, which is end up taking the square root term, getting rid of that. And then the middle two terms, the O and the L of FOIL, those go to 0 because they cancel each other out. And then you have the last term, which is -5, because square root of 5 times square root of 5 is 5. Negative times positive is negative. And then you have the denominator, which we don't fool with at this point. Okay, so what can we do here? Well, that and that are opposite negatives of each other. So those cancel out. This can drop that. So we just end up with x by itself. So that x will be canceled out with the x in the denominator to get 1. And so ultimately the expression that we're going to take the limit of as x goes to 0 is 1. So when you cancel that out with that, you get 1. So you get 1 divided by the square root of x plus 5 plus the square root of 5. And then this is determinate, whereas this was indeterminate. So so now we just plug 0 in. And what do we get? We get 1 over the square root of 5 plus the square root of 5, which is 1 over 2 times the square root of 5. So that's your answer. We'll go ahead and multiply it by the square root of 5 divided by the square root of 5 to get that out of the denominator. And so we get the square root of 5 over 10. 2 times square root of 5 times the square root of 5. These two multiplied together give us 5. 2 times 5 is 10. And so that would be the answer to that problem. And I'm pretty sure I did that right, so I'm not even going to look it up in the answer book. Okay, where are we? 53. So 53 is a case of where you have to use rationalization. It always happens when you have some square root kind of thing. So you can't factor this. But if you do plug in, again, if you plug in the number here that you're taking the limit towards, so if I do f of 4, where this is the function, you have square root of 4 plus 5 minus 3 divided by 4 minus 4. And so you get the square root of 9, which is 3 minus 3 over 4 minus 4. And so you get an indeterminate result again. So since we can't factor this, we have to use the other technique, which is called rationalization. And basically all you have to do is you take the term that involves the rational, which is the numerator, and you multiply it by the radical part, and you change the sign on the other part. So I'm going to actually take I'm not going to put the limit up here until I get it simplified. We're going to take the original equation, original function, in this case what I'm calling f of x, put in parentheses because we're going to end up using FOIL. So the original function is the first two terms here. And then you multiply it by 1, but 1 is any number divided by itself. So what we do is we take the rational part, the radical part, and we add 3 instead of subtract 3. And what that's going to do is it's going to make it so that we can cancel some terms out just like we did in the other case. Okay, so we do use FOIL. And we're kind of used to having x plus, x something. But I'll use the same procedure FOIL. It's just, in this case, this square root of x plus 5 times the square root of x plus 5 is just x plus 5. When you multiply the square root of something by itself, that same term, it becomes just a term in the parentheses. Now, because you chose a sign opposite, what's going to happen is the O and the I, the middle part of FOIL cancels out because you get plus or negative 3 times this and positive 3 times that. And so the second term is, I'll just write it out. So you get negative 3 square root of x plus 5 plus 3 times the square root of x plus 5. And so those cancel out, so you don't even need to write them down. And then you have the last term, which gives you negative 9. And it turns out that when you use rationalization and your original expression is indeterminate, then the denominator term after simplification cancels out with the numerator term. So these have gone. So then you have x plus 5 minus 9, which is x minus 4. So you have x minus 4 square root of x plus 5 plus 3. So now you got this common term, cancels out, and so we end up with 1 divided by the square root of x plus 5 plus 3. So that's my original function simplifies down to this, and this expression is not indeterminate when you evaluate the original limit. So when you take the limit as x goes to 4 of 1 over the square root of x plus 5 plus 3, and you plug that in, you end up with 1 over the square root of 4 plus 5 plus 3, which is going to be 1 over 3 plus 3, which is going to be equal to 1/6. So that's the limit, is 1/6, even though when we originally just plugged it in, we got 0 over 0. Again, you have to use this modified method. kind of like the complex conjugate of complex numbers. And again, we can go back to we go to the graphing program and just do the same thing graphically. So let's do that. So we have the square root of x plus 5 minus 3 divided by the quantity x minus 4. Now if we push the standard button, it just changes to 6 by 5. You can actually see a little bullet here at x equals 4, and if I zoom in and I disappear, zoom in on it. So we're looking for the limit as x approaches 4 of that function. And you can see that graphically the limit goes to right there, and you get 0.164. And if you look at the original answer was 1/6, which is 0.166666. So it's just because if I zoomed in on this thing continually, didn't want to do that. How do I go back one step? Can't remember. Oh well. Anyway, if you have to make sure I keep the 4 in the screen. So there's 4, and if I zoom in on that too exactly and see it's 0.1667. Okay, let's see, where are we here? We're in problem 56. So this is another rationalization problem, possibly. We always have to check to see whether the function exists, and if it does, then we don't have to worry about it. Notice one thing about these functions that we're doing. You think, are we really going to use those things? Well, the answer is yes. Okay, so this does get used. So we're not just doing it as something to keep us happy. Anyway, so if you plug in x equals 3, you'll get 3 plus 1, which is 4. Square root of 4 is 2, so you get 2 minus 2. And if you plug 3, 3 minus 3 is 0. So it is, if you do that, you get 0 to 0. So it is indeterminate. And likewise, as we did before, I'm just going to look at the function, the original function, and then we're going to do what we did last time. Put parentheses around these because we're going to do FOIL. And then you take this expression, keep the rational part the same, change the sign of the second part. So instead of subtracting 2, we add 2, and you do this in both the numerator and the denominator because that's the same as multiplying by 1. One thing to note is, think about this, the range or the domain of this particular function is the allowable x values. So what is the domain? Well, the domain is x has to be greater than -1, because if x is less than -1, then this is a negative square root. So we know it's greater than -1, and we also know that when x equals 3, that we get an indeterminate result. So the domain goes from -1 to positive, just less than positive 3. So let's write the domain out just as a review. The domain would be, let's see, x is greater than or equal to -1, because that can go to 0. We just can't have it being negative. And then it is going to be less than 3, and then it goes from 3 to infinity. So that's the domain of that particular function. This because you get a negative square root, and this thing here because it's undefined, it's indeterminate. Okay, back over here. So we multiply this thing out. So the first term, when you multiply the square root terms together, you get just the expression, which is x plus 1. The 2 middle terms drop out, so I'm not even going to put them in there. And then you have the 2 last terms multiplied together, which would be -4. And we don't do anything with the denominator yet. You can see that this is x minus 3 when we do these 2 terms, and those cancel out. So the function that we are going to ultimately do the limit on is 1 divided by the square root of x plus 1 plus 2. So we can go back over here. Let me just move this domain stuff out of the way. So this original limit we can put in as the limit as x approaches 3 is the same as 1 divided by the square root of x plus 1 plus 2, and then you just plug the number in. So you'll have 1 divided by 3 plus 1 is 4, take the square root of 4, it's 2, so this becomes 2, 2 plus 2 is 4. So the answer is 1/4. '63. So 63 and 64, actually we haven't gotten to the trig function things, but the trig function is either just plug the numbers in or you have to use the squeeze theorem. Anyway, that'll be the next group. But we have 63 and 64, which say in exercises 63 through 66, use the graphing utility to graph the function and estimate the limit. Use a table to reinforce your conclusion, then define the limit by analytical methods. So we're just using all three methods that we've learned so far. So we have the limit as x approaches 0 of the square root of x plus 2 minus the square root of 2 divided by x. So if you plug the number in 0, you're going to get square root of 2 minus the square root of 2 over 0, which is 0 divided by 0. So it's an indeterminate result. So let's do the first graphing utility. So we're going to go over here and switch to the graphing utility. And we're going to just plug the equation in. So square root of x plus 2 minus the square root of 2 all divided by x. And we're looking for the limit as x approaches 0. So we see a limit coming up here. It's right there. And it looks like y is equal to 0.353. So let's go back to I'm going to write this down on our page. So graphically, this is equal to 0.352, I think. Okay. Numerically, all you have to do is just take some numbers near 0. So we could say x is equal to negative 0.01, for example. And then you just plug it into your equation. So you have the square root of negative 0.01 plus 2 minus the square root of 2 divided by negative 0.01. So get the calculator out. So we have the square root of negative 0.01 plus 2, close parentheses, minus the square root of 2. Okay, so that's the numerator. And I get 0.00354. And I divide by negative 0.01. And I get 0.354. And if I took a number very close to 0, but on the other side, plug those in, I'd have 0.01 plus 2 minus the square root of 2, all divided by 0.01. And if you do that, let's see what we get. Square root 0.01 plus 2 minus square root of 2 divided by 0.01. And I get 0.353. So it looks like the answer is going to be somewhere between these two values. So the last thing is to do it analytically. So what I'm going to do is add a page in here. and we use rationalization. So I'm going to just do the function by itself, and then I'll apply the limit. So we multiply by the square root of 2x plus 2 plus the square root of 2, all divided by x. So this is my original function, and then I have this term that I have common to both the numerator and the denominator. Anyway, so we don't cancel those out because we just stuck them in there. And then you multiply it out. So f, first term, becomes x plus 2. The inner and outer becomes 0, and the final one becomes just 2. Square root of 2 times the square root of 2 is 2, and you have a negative sign. And the denominator, we have x times square root of x plus 2 plus the square root of 2. And you see the numerator becomes x, and the denominator has an x. And then we have this extra term we introduced. So these cancel out, become 1. So the function can be rewritten as such, and it is exactly the same, except this function is continuous, and so we can, I just realized I think I wrote that wrong. There we go. So anyway, you get x plus 2 plus the square root of 2. So that's my function, kind of my modified function. And so the original limit of the original function is the same as this modified version. 1 over the square root of x plus 2 plus the square root of 2. And so when you plug 0 in, you get 1 divided by the square root of 2 plus the square root of 2. So you get 1 over 2 square root of 2. And if you wanted to multiply both the numerator and the denominator by the square root of 2, you'd end up with that. Okay, so multiply this by the square root of 2 divided by the square root of 2. So I get the square root of 2. 1 times the square root of 2 is the square root of 2. Square root of 2 times the square root of 2 is 2. So I end up with the square root of 2 over 4. And if I plug that into my calculator, sorry, square root of 2 over 4, not square root of 4 over 4. So the square root of 2 divided by 4 is 0.35355, blah, blah, blah. So you see all three cases we came up with the same answer. So graphically we got 0.352. I think I might have just read that wrong, slightly off. Numerically, we just plugged in numbers close to 0, and we got close to the right answer. And then the analytical one is the exact. Okay, so we're on to 64 now. So let's just write it down. The limit as x approaches 16 of 4 minus the square root of x divided by x minus 16. So you plug in 16, you'll get 4 minus the square root of 16, which is 4. 4 minus 4 is 0. 16 minus 16 is 0. So it is indeterminate. And we're supposed to use the three methods. So graphically, we're just going to plot this function. And I need to remember to switch over my sharing here. And so let's put it in here. 4 minus the square root of x divided by x minus 16. Graph, let's put it standard zoom. So there we go. Notice the function does not exist below x equals 0 because then you have a negative square root in the numerator. At x equals 16, I can't see 16, so I'm going to zoom out in the x direction. So you see 16 somewhere around there, and it's going to be like negative 0.14. Let's just zoom in here. Make sure we keep 16 in the viewing window. So there's 16. I come up to the function. I get negative 0.127. Okay, so let's go back. Negative 0.127. Negative 0.127. Negative 0.127. So that was what we did graphically. Okay, numerically. Numeric. Okay, so we're just going to find some numbers near 16. So let's use x equals 15.9. So plug that into our equation. So f of 15.9 is 4 minus the square root of 15.9 divided by 15.9 minus 16. And we go to our calculator. 4 minus square root of 15.9. And then we divide that by negative 0.1. Negative 0.1. So we get negative 0.125 something or other. Okay. And if we did it for x equals 16.1, we get something that's close enough for right now. So you can see we just take numbers real close to 16. The closer you are to 16, the closer this number is to what we got graphically. Analytically, this is the third kind, and analytically we use rationalization. So I'm just going to take the function, say f of x is equal to 4 minus the square root of x over x minus 16. And then we multiply by 4 plus the square root of x over 4 plus the square root of x. Now, I could have used negative 4 minus the square root of x. It doesn't matter. I just chose it so that I think I'd end up with something positive. Okay, so when you multiply the numerator out, you get 16 minus x. 4 times 4 is positive 16. Negative square root of x times positive square root of x is negative x. The denominator is x minus 16. 4 plus the square root of x. So these are almost identical. If I factor out a negative 1, the numerator could be negative x minus 16. Okay, so then they cancel out. So f of x is negative 1 over 4 plus the square root of x. So now this is not indeterminate. This is our original function. This function is going to look exactly like this one, except at x equals 16, it's going to be determinate. So all we have to do is find out what the limit of this new thing is. So now we just plug the number in, so we get negative 1 over 4 plus the square root of 16, and so we get negative 1/8, which we all know, and we don't all know, negative 0.125, exactly. So you can see numerically we got pretty close to it, and graphically we got pretty close to it too. Okay, so we're going to move on here to trig functions. There's really nothing different except that we can use the squeeze theorem to evaluate results that are indeterminate. So some of these are indeterminate, and I think some of them are just plug in the numbers. So number 67 says the limit as x approaches 0 of the sine of 5x divided by, pardon me, not 5x, just x. Divided by 5x. So if you plug 0 in, you'll get the sine of 0. So we're just plugging in. That's always our first step. Plug it in and see what happens. So you get the sine of 0 divided by 5 times 0. Sine of 0 is 0, so you get an indeterminate result. So the squeeze theorem says there's two parts of the squeeze theorem. One says the limit as x approaches 0 of the sine of x over x is equal to 1. And that's because as x goes to 0, so as x goes to 0, the sine of x approaches x. So they end up being equal to each other, which when we get into infinite series in the second semester, you'll see why that is true. So since they approach each other, the ratio, that's one way of looking at it. There's, we covered the more, what's the word, mathematically correct way of looking at it. Anyway, but we have the squeeze theorem result. So we go back to the original expression. We said we don't have exactly that, but constants don't really affect anything. So we could say that the limit as x approaches 0 of the sine of x over 5x, you can kind of factor out the 5. So it's 5 times the limit of the sine of x over x as x approaches 0. And the squeeze theorem says that this is 1. So we can substitute in there. So it's 5 times 1, so it's 5. Divided by 5. So it's actually 1/5. Sorry about that. At least I caught it before it was too late. So you get 1/5 times 1, which is 1/5. Now, I'm not sure if there's one like this, but I'm going to mention it anyway. So what would happen if I had, what is the limit as x approaches 0 of the sine of 5x over x? Well, in this case, you'd say, well, I don't have different things here. So is it possible that I could multiply by 5 and divide by 5? What would happen there is if I multiply, so we just do that within this limit expression. So I'm going to multiply by 5, so I've got 5 times the sine of 5x, and I divide by 5 times x. So here's 5 divided by 5 is 1. And just like before, I can factor the 5 out. So I have 5 times the limit of the sine of 5x over 5x. Well, as long as this argument here is the same as this, then you can use the squeeze theorem. So this is the kind of the basic form of it, but I could have the sine of 1,000,000 x divided by 1,000,000 x, and that would be 1. So as long as these two quantities, this value and this value, are the same, then this is true. So in this case, it would be equal to 5 times 1, which is equal to 5. That's it. Okay, what are we on? 69. Okay, so we have the limit as x approaches 0 of the sine of x times 1 minus cosine of x divided by 2x squared. So there were two squeeze theorem things. There's the one involving the sine and the one involving the cosine. So the one involving the sine we've already looked at. Which was this one, and then the second one was the one involving the cosine, which is actually 1 minus the cosine of x divided by x, and that's equal to 0. So what happens is x approaches 0, this number approaches 0 more quickly than this does. And because it approaches more quickly, then ultimately this part is much smaller than this part, and it approaches 0. That's kind of the idea graphically, if you think about it. So Anyway, what we're going to do is we have to just do a little manipulation of this expression up here and try to write part of it like that and part of it like that, because if you have the limit of something times something, it's the same as the limit of something times the limit of something. So you can break it up into two parts. So what we would do is we would factor out the 2, and then you take one of these x's that makes up x squared, and you would put that with the sign of x, and then you would do the limit as x approaches 0 of the other part, which is 1 minus the cosine of x, and that divided by x. So if you look at these two, you can see the same thing. Once you multiply them all together, you get sine x, 1 minus cosine of x, divided by 2x squared. And then these can be treated individually. So the first one goes to 1, so this becomes 1 based on that. And the second one goes to 0, and since there's a 0 in there, everything equals 0. So the whole thing goes to 0. Okay, let's see where we are. 72. So let's see, we have the limit as h approaches 0 of 1 minus cosine of h squared over h. So again, we're going to break this down into two parts. It's not 1 minus cosine of h over h squared, so we can't just break it into two parts, but we can break it down. We can say it's the limit as h approaches 0. So we'll take one of the square terms, and then we'll break it apart. And do that. So multiply those together, you get that. And so the first part, we can evaluate. So the first limit, we just plug it in there, because it's the reason we don't, if we plug 0 in here, we're going to have 1 minus the cosine of 0. Cosine of 0 is 1, so you get 1 minus 1, which is 0. So you get 0 squared over 0. So initially, you get 0 over 0. So if we can break this up so that the indeterminate part, which is this part, goes to something other than being a determinant, what's left over, if we can just evaluate that, and it's not indeterminate, then we're in good shape. So the first part, we just evaluate that, 1 minus the cosine of 0. And the second part, we use the squeeze theorem, which says that is equal to 0. And you could just say that's 0, the answer. The answer. You'd also go one step further here. The cosine of 0 radians is 1, so you get 1 minus 1 times 0, which is just 0 times 0, which is also 0. Okay, so let's see what problem we're on here. 72, I think. 72. So we have the limit as x approaches 0 of the tangent squared of x divided by x. So you look at that first and say, well, the squeeze theorem involves the sine and the cosine, so what am I supposed to do? Well, let's do one thing. Let's prove that it's indeterminate. So if you just evaluate this limit, put 0 in, you get the tangent of 0 squared divided by 0. The tangent of 0 is 0, so you get 0 squared over 0. So it does become indeterminate, so we don't know what's going to happen. So you're going to have to use some kind of trig identity. And there's a couple where we had, well, first that the tangent of x is the sine of x divided by the cosine of x. We also had, and I always forget the other one, I think after all these years, but that's the one I remember. So if you divide by the sine squared of x, sine, actually we want to divide by the cosine. because that gives us a little bit. Anyway, if you divide by the cosine squared of x, cosine squared of x, cosine squared of x, that sine over cosine is tangent, so you get tangent squared of x plus 1 is equal to the secant squared of x. So you could solve for tangent squared and plug it in there, which would be secant squared minus 1. That would be one way of doing it. Or you could just plug in sine over cosine. So I think I'm going to try just sine over cosine. So instead of tangent, I'm going to have the sine of sine squared of x divided by the cosine squared of x, and that whole thing is divided by x. Okay, so when you divide something by a fraction, you take the reciprocal of that, and that's, let's see, are we doing that right? So let's see what we have. So you're dividing this by that, so you take the reciprocal of that, and so reciprocal of x over 1 is 1 over x. So you end up with sine squared of x divided by x times the cosine squared of x. Okay, so now what's happening? Can we use the squeeze theorem? Well, yeah, because what we can do is we can take one of these sine of x's. So what we'd have is the limit of the sine of x divided by x, so that's one of these and that, times the limit of the sine of x times the limit of 1 over the cosine squared of x. So the question is, are any of these individually indeterminate? Well, without using the squeeze theorem, this one is indeterminate, but we can use the squeeze theorem to say that's 1. And these are all as x goes to 0. So that's the first one. The second one is, what's the limit of the sine of x? Well, this is just a continuous function, so it's just the function, so it's the sine of 0. And then the third one is 1 over the cosine of 0 quantity squared. So the sine of 0 is 0, and then you get 1 over 1. Cosine of 0 is 1, so you get 0. So it's not indeterminate anymore. It actually equals 0. Our last problem in section 3 is 75. So we have the limit as x goes to pi over 2, and we have the cosine of pi over 2 divided by the cotangent of pi over 2. So again, the first thing you do is you plug it in, and remember from the unit circle days that the cosine of an angle is equal to the x-coordinate, and you have your circle here, unit circle. So this is pi over 2, x is 0, so the top's going to be 0. Now the cotangent of theta is equal to the cosine over the sine. So then you plug in the values there. So the cosine of pi over 2 is 0, and the sine of pi over 2 is 1, so it's 0. So you do get an indeterminate form. So one thing we can do is probably just rewrite the cotangent as cosine over sine. So you don't have to use the squeeze theorem all the time. You can just use trigonometric identities to simplify. So you've got the cosine of actually I should have put x. Cosine of x divided by the cosine of x divided by the sine of x. And again, if we're taking this, dividing by that, it's the same as multiplying by the reciprocal of what's in the denominator. So you get cosine of x, which is this, and then you take the reciprocal of that, which is the sine of x, divided by the cosine of x. So these cancel out, and you just end up with the limit as x goes to pi over 2 of the sine of x, which from over here we know was equal to 1. And that's the answer. Now we're just going to show you one other thing here on this last problem, just to show you how you can kind of see what's happening if you go to the graphing program. So let me open that up and share that with you. Okay, so here's the graphing program, and so we're looking at the limit of the cosine of x divided by the cotangent of x. And, okay, so graph. So when you look at it, it looks exactly like the sine of x. That's the same. If you plotted the sine of x, so put sine of x in there, graph that, you can see it's exactly. And so what's the difference? Well, the difference is that the original function has the cotangent of x, which goes to 0 at certain points, which doesn't. The sine of x has a domain of all real numbers, whereas the cotangent has cases where it goes to 0, and therefore when you divide by 0, 1 over the cotangent, which is the tangent, has vertical asymptotes. So they look the same, except there's going to be some cases where you're going to have an indeterminate result, which is what happens at pi over 2, which is right here. You can't tell because it's just a point, and the point has no width to it. So anyway, let me go back here again. So rather than print, so you can see the answer is 1, which is what we got. But if you plot the cosine of x and the cotangent of x separately, it looks like that. So you see that they're both 0. The cosine is 0 and the cotangent is 0. And so it's indeterminate. But if you zoom in on this, is that you can see as you approach pi over 2, which is right here, that the two functions approach each other. So in that case, since the numbers approach each other as they go to 0, then they are going to be, the ratio of the two is going to be 1. Right here, they're indeterminate because they go to 0. But if you're right, very, super close to it, they map on each other, just like x, the sine of x and x. Let's go back to that one. So if I plot the sine of x and y equals x. So y equals the sine of x and y equals x. And you can see that when they're away from 0, they're not anywhere near close to each other. But as you get close to 0, they end up sitting right on top of each other. So as x approaches 0, the sine of x and x, those two functions are identical to each other. And at 0, they are the same.